Now coming to the speakers for today, our first speaker is Eliot Jager, who recently finished his PhD thesis at the IGE in Grenoble, and now he has started a postdoc at the University of Helsinki and is working on ice-ocean interactions in Antarctica. And today he will present the results of his thesis, which focuses on the validation and quantification of uncertainty in a Greenland ice sheet model with satellite data. So welcome, Elliot.
Yes, hi. I share my screen. Can you see my screen?
Yes, looks good.
Yes, okay, perfect. So I'm starting. Hi everyone. So yes, I'm Eliot Jager. I'm currently at the University of Helsinki, and previously I was at IG in Grenoble. And I will present you the results of my first paper, where I try to do some validation of historical reconstruction simulation. We know today that the sea level is rising, and we have different contributors of this sea level rise: the ocean expansion, the glaciers, the Greenland ice sheet, and the Antarctic ice sheet. And we know that for the future, the highest uncertainties are coming from the two ice sheets, the Antarctic ice sheet and the Greenland one. Today, to quantify these uncertainties, the state of the art is the ISMIP6 project. So here you have on the left the impact of the choice of the climate model on this projection, and so you have different climate models which give different range of sea level projection. And on the right, you have for one climate model what are the results from the different ice sheet models. But today we are not sure about the ability of the different ice sheet model to reproduce past observation. So on this figure, you have in blue the observation, and in gray the different number from ISMIP6, and you can see that there is quite a big gap between the observation and the models. There is really a few of them which are able to reproduce the past observations. And so during my PhD, I used Elmer ice, and I tried to see if I can bridge the gap between the observation and the model. So today I will present the result of two main questions. First, how can we validate our ice sheet model? Which data we can use and which tools? And secondly, what are the main processes we have to take into account to reproduce the past observation? So I focused on Upernavik Isstrøm, which is one of the which is a Greenland tidewater glacier located here in Greenland, the red catchment. Why did we choose this glacier first? Thanks to ISMIP6 project, we know that for Greenland, the largest uncertainties are situated in the tidewater glacier areas. Secondly, here you have the mass loss from the different sector. So when is when, so everywhere. And we can see that the largest mass loss during the past decades were located in this north sector area, in this northwest, sector. And in this sector, Upernavik Isstrøm is the biggest glacier, and it has contributed to 4% of the Greenland's contribution since the 80s. We have also quite a large amount of data for this glacier. So here the ice is flowing from right to left. And we have multiple glaciers in one catchment. And so for doing some validation of a model, it's quite interesting because you have different behaviors. And if your model is able to reproduce all of these behaviors, yes, it's more robust. So first we have collected some front position, and we can see then the front of Upernavik Isstrøm North and Center retreat around 2005 for this one and 2010 for the center one. Because the front retreat, you release some stresses, and so you have an increase of the velocity. You can see it on this figure where we have the velocity in function of time, and for the Upernavik Isstrøm North, you can see a large increase in velocity when the front retreat around 2005, and same for the center around 2010. Because you have an increase of the ice velocity, you have an increase in ice discharge, and so the glacier lost more ice. And because you are losing some ice, some mass, you have a decrease in the surface elevation. In this one, you can see for Upernavik Isstrøm North, then the surface elevation is quite constant until 2005, and after you have a break in the slope, it decreased a lot, and after it's quite constant again. And so we try to see with MRIs if we were able to reproduce these changes between 1995 and 2019. So we have different components in the model, and we take into account the uncertainty of the different on the different box and see the impact on the output, and if we have some results which are in better adequation with the observation. So just to summarize our method, first we have done some uncertainty quantification of the different model parameters, but also about the calibration and the initial state of the glacier and the forcing. Secondly, we have doing some ensemble friction calibration with observed velocities from the 2010 year. After we have doing a small simulation to obtain an ensemble of initial geometries in 1985, and finally we run the ensemble between 1985 and 2019. And we prescribed surface mass balance and the front position, and then we can compare with observations. So second question, what are the main processes we have to take into account to reproduce the past observations? Just a small recap, a small summary. There is different type of friction law. A friction law is the relation between the basal shear stress and the basal velocity. You have mainly two family of friction law. The first one where you don't take into account the subarctology, and you have the basal shear stress, which is a function of the velocity, and a second family where this time the basal shear stress is a function of the velocity and the effective pressure, which is the difference between the ice pressure and the water pressure at the interface between the ice and the bedrock, and also a friction parameter. But to compute this effective pressure is quite expensive numerically. So in reality, we cannot use that for future projection with our model. So I found quite a compromise between these two families by taking into account the fact that the friction coefficient is going to zero at the grounding line due to this effective pressure. So I've tested two different ensembles. First one with a constant friction field. So it's only dependent on the velocity. And the second one where this time the friction field, sorry, depends on the distance to the front. And so it evolved with time. So here you have the result from the two ensemble, in blue with the constant friction and in red with the ensemble where the friction evolves in times in function of the distance to the front. And you have different observation data sets. And first we can see that the ensemble with the constant friction is not able to reproduce the full acceleration of the glacier around 2005. There is a small increase of ice discharge. Secondly, we can see that the constant friction ensemble is not able to reproduce the initial ice discharge. It overestimates this initial ice discharge. And so now we will see why this ensemble overestimates this ice discharge. So here you have a bias map for the two ensemble. When it's purple, so in 1985, at the beginning of the simulation, when it's purple, it means that the models overestimate the observation, and when it's green, it underestimates the observation. And we can see that the overestimation of ice discharge is coming from this glacier, the Upernavik Isstrøm North, where we have a really high bias, positive bias of the model. Whereas then for the other ensemble, the bias is really less important. Last things we can do, because we are doing some uncertainty quantification, we can see inside the shading, the ensemble, what is the main causes of this variability between lower members and higher members of the ensemble. And so what we found is that the uncertainty of the ensemble is mainly causes by uncertainty in the model parameters and in the calibration of these model parameters, whereas then the forcing and the initial states are really small impact on this reconstruction. And it's not, of course, for our future simulation, we won't have the same result. So just to summarize of all of this, the goal was to bridge the gap between observation in blue and our model MRIs. So we have developed some validation tool, and we also collect a large amount of data to validate our model. And we have also done some uncertainty quantification of MRIs and we have created a new parameterization for the friction to take into account the subhydrology. Finally, we obtain something like that, where we have the ensemble in gray, and the different cross are the observation for Upernavik Isstrøm. And so now our model is able to reproduce past mass changes of Upernavik Isstrøm. And the next step will be to see what are the changes in the future for Upernavik Isstrøm. And our two main results is, first, with spatial data, we can provide more information if we want to see clearly where are the bias of the model, where they are located. And secondly, then to reproduce the past changes of a tide water glacier, we have to use a friction law that considers subhydrology, subglacial hydrology. And that's all for me.
Thank you very much for this nice talk. Yeah, as always, we are having questions at the like after the three speakers gave the talks. So yeah, I would just then directly move to the next speaker for today, who is Benjamin Wallis. And Ben is a PhD student at the Institute for Climate and Atmospheric Science at the University of Leeds. And he studies ice dynamics in the Antarctic Peninsula to using remote sensing. Yeah, hi, Ben.
Thanks, Mark. Just get going here. How's that?
Looks good.
Great. Yeah, hi everyone. Just start by saying thanks to the organisers for organising the seminar series, and thanks to Elliot for his talk, and I'm also really excited to see Kaian's talk as well. Normally I watch the seminars on YouTube later rather than 9 o'clock at night in the UK, but it's nice to be here on time for once. Yeah, so I'm Ben. I'm a PhD student at Leeds. I'm supervised by Anna Hogg, and just to introduce myself a little bit, because I think most people on the call probably haven't met me before. I did physics originally for my first degree, and then I worked in industry for a little while before starting my PhD in 2020. So I'm due to finish imminently. And in this talk, I'm going to try and synthesize the main aspects of my PhD work that I've done over the past 3 years, looking at the Antarctic Peninsula, and just take this opportunity as well to thank my supervisors, Anna Hogg, David Hogg, and Mal Macmillan, for their support, and also all co-authors who contributed to the work that I'm going to present in this talk as well. I'm always grateful for their support. So let's start by talking about the Antarctic Peninsula. So I realise not everyone maybe not be familiar with the AP. It's a small region of Antarctica, but I'm going to hopefully convince you by the end of the talk that it's interesting, it's important, and it's a worthwhile place to study and can teach us some interesting things. And I'm going to try and put my work in context with the story of the AP's evolution throughout the remote sensing period, so sort of the recent period. And if you kind of ask me why the Antarctic Peninsula, which sometimes people do, they say in one line, say it's interesting because it's a region that's full of contrasts. It's this huge mountainous spine. It's over 1,000 kilometers long, but in some places it's only 40 kilometers wide. It's got tidewater glaciers on the west coast. It's got huge ice shelves on the east coast, and it's got these two really distinct ocean masses. You've got the warm West AP Shelf and Bellinghausen Sea, like the cold, ice-dominated Weddell Sea on the east coast. It's the warmest region of Antarctica. Summer temperatures get above freezing pretty regularly. It can rain there. There's a lot of melt. There's also huge amounts of accumulation on the spine because of that orographically driven precipitation. So it's like a really interesting extreme environment, which makes it exciting to study. It's also interesting because it's changing very rapidly. Since in the remote sensing era, and that's kind of the framing that I'm going to use, the AP's lost huge amounts of ice shelf area. It's one of the only places where we've monitored, seen the catastrophic collapse of an ice shelf in real time, been able to monitor the subsequent evolution of glaciers afterwards. Its tidewater glaciers on the west coast are retreating. Its ice mass loss has increased. And it punches above its weight in terms of sea level rise, despite being a really small part of Antarctica area-wise and total ice mass-wise. It's contributed 14% of Antarctica's total sea level rise contributions in the last 30 years. So it is important to contemporary sea level budgets. And another thing that's interesting, I think, is that these changes have been linked to climate change pretty closely. So the warming atmosphere is thought to have caused more melt ponding on ice shelves, hydrofracture of crevasses, collapse of the ice shelf, and then the loss of buttressing to glaciers, hence the ice mass loss from the grounded ice sheet. And on the coast, the warming ocean on the west coast, where that's exposed to circumpolar deep water, that's been shown to be linked to the retreat of glaciers that are exposed to that water mass. So that's why I think about the AP and I think it's interesting to study. But my work, specifically what I do, so I do ice dynamics from remote sensing. So to put it in a nutshell, that means measuring what the glaciers are doing from satellite imagery. Primarily I want to measure the AP in the highest possible spatial and temporal resolution in the current period. And we're in many ways in an era of way more satellite observations than we've had in the past. We get huge amounts of data all the time. And what can we learn about what's going on in the peninsula from these huge amounts of data? And how can we leverage them to really understand what's going on? And my primary data set throughout my PhD has been velocity data. And so to talk about just kind of how we do it at Leeds, at Leeds we routinely process every Sentinel-1 acquisition for ice velocity over Antarctica. I've processed the peninsula specifically, but other members of our research group done the rest of Antarctica. For the peninsula, this means over 10,000 image pairs to about 2022, I think that is, 40 terabytes of data just for this small area. Over 100 glaciers in the peninsula that we can study with this. So 100 time series, 100 things that could be going on. We generally tune our tracking parameters for each area, so we treat the peninsula the same as the rest of the air sheet. And we use Bayesian recursive smoother to post-process our ice velocities to account for the quality of the measurements and errors. And so if you do this, if you process all the ice velocity data for the peninsula, you do that everywhere, and what do you find? Well, you can find some interesting things. So the first sort of major thing that I found during my PhD, which kind of kicked off a lot of the other work that I've done since, is seasonal ice speed variability on the west coast of the peninsula. So here's a few examples of these trends in our data. This is the raw data and smooth, so warts and all. We find that on average, glaciers on the west coast speed up by about 12% a year, but it could be up to 22% on the ones that have the strongest seasonal signals. We see a summertime increase in ice speed and slow down throughout the winter period until the next melt season. And these patterns are strongest in the north of the peninsula, but we do see glaciers towards Marguerite Bay also exhibiting this behavior. And until we had this data, we didn't know these trends existed. So it was an exciting development, and it was, it's been really interesting to investigate these. And we want to know not just that these are happening, but why and what the implications are for perhaps the ice dynamics for the peninsula in the future. So what I did next was I compared these two some environmental forcing. So if you take Shahateet Glacier, which is the bottom here, which is the glacier that has some of the largest seasonal speed variability in the peninsula, we plot it next to some environmental factors. So we've got surface water from the Rackman Regional Climate Model, we've got terminus position, painstakingly digitized by me, and got ocean temperature anomaly from reanalysis. That's the upper ocean, seasonal part of the ocean temperature cycle, which seems to be a proxy for frontal ablation as well. And what we find is that these speed trends do correspond to these forcing mechanisms. And for example, in 2020, across the peninsula, that's the highest melt year in this time series. And that's also when we saw the largest speed increases on the majority of glaciers. What's interesting in this that you might be able to spot is that peak melt and peak speed are slightly lagged. So peak speed happens a little bit after peak melt. And that was a bit of a mystery for a while. So to investigate that, we need to take a step back and look at the basin scale of these speed trends rather than just individual glaciers or a handful of glaciers. So if you kind of try and plot a whole coastline of glaciers on one plot, you might get this. And this is a little bit complicated, so let me explain this plot. This is a histogram of the timing of peak speed for 105 glaciers up the coast of the peninsula in every year from 2014 to 2021. So if the peak speed is in February, that's in the February bin. And so red is peak speed and blue is speed minimum. And the 20 most seasonal glaciers are the dark shading. What you can see is that this pattern of peak speeds in the summer, minimum speeds in the winter is widespread across the whole peninsula. And when we compare that to not just melt, but runoff in the Rackman climate model, which we can assess at basin scale a bit more reliably than individual glaciers, because the pixels are sometimes bigger than glaciers. See that while melt peaks around the turn of the year, runoff actually peaks in February when we find most glaciers are having their peak speed as well. And so that can help to explain that disparity. And it just shows you how important potentially the fern pack is around the peninsula to behavior of some of these glaciers, in that it buffers that surface melt and slows it down before it becomes runoff, because it can retain some of that water. But this in some ways assumes that melt reaches the bed to force the glaciers down. Do we know that that's happening? On the mainland peninsula, there's obviously a shortage of it's very inaccessible, despite being quite close to a lot of stations. People don't routinely go there. But one thing we can look at remotely is sediment plumes. So sediment plumes caused by meltwater at the bed, from the bed being released to the ground line and rising to the surface because it's fresh and buoyant, carrying sediment with it. You can see these in satellite images. These are well observed and studied in Greenland and Svalbard, say, but a few observations of them in Antarctica, particularly on the mainland. And we find these plumes dotted around the peninsula, which gives us some confidence to say that we think melt potentially does reach the bed. And some work I've been doing more recently is to develop an AI model to delineate these plumes in images, so we can form a full time series without having to manually delineate 7 years worth of satellite images, a lot of which are cloudy. And this when we frequency map, this is Brabant Island on the west coast. And I'll be presenting this work at EGU this year. So if you'd like to hear more about it, you can come and find me there. I'd be very happy to talk about it in more depth. And one last thing to touch upon, as well as those seasonal trends, we also see some long-term changes in the Sentinel-1 period, so from 2014 to present in the peninsula. This is an increase in ice discharge from the peninsula, particularly the west coast. So one example of a glacier that has the biggest change in discharge in this period is Kaian Glacier, which increased its discharge by 28% in just over a year, which is a huge amount. It increased speed by over 1,000 meters a year in some parts of the glacier. And the whole of the West AP, this is some work that a colleague of mine, Ben Davison's been doing at Leeds that I've been helping him with. On the whole of the West Coast, discharge has increased by 7% since 2017. So there is this widespread trend of increasing discharge as well. And both these instances we think can be linked to periods of anomalously warm ocean water on the west coast, which kind of shows you the role of the ocean as well as the atmosphere enforcing ice dynamics in the peninsula. So I'm just going to kind of summarize a little bit and talk about what I think the interesting points about the peninsula and kind of how things have changed recently. The observed new patterns of seasonal ice peak variability. There's also been observations further south on Georgia's 6th ice shelf by Carla Boxall at Cambridge Uni. We've seen significant increase in ice discharge since 2018. And interestingly, recently, a paper that just come out showed that atmospheric warming has kind of restarted in some ways on the peninsula since in the last decade. Glaciers and ice caps on James Ross Island, which had quite stable mass balance for the previous decade, are now in the most recent decade negative again. So in many ways, the peninsula is changing quite rapidly at present. And I think this reflects kind of the competing influence of that warm ocean on the west coast and the atmosphere as well, and how that balance of forcings will change in the future is, I think, a really interesting question. Melt from the AP was projected to increase in all emission scenarios. So it's possible that if melt does reach the bed, as the evidence in my work suggests that it does, that could have an impact on ice dynamics in the future on the peninsula. And I think that's particularly relevant considering that the kind of late summer switch to efficient drainage and ice slowdown associated with melt that we see in Greenland. We haven't observed that in the peninsula yet. We haven't found any instances of it. So if that happens or doesn't happen, potentially that's quite an interesting question to ask, is if that feedback that appears in Greenland, will that happen on the peninsula in the future, or is it sufficiently different to make that not important? Yes, so I'll just do the summary rather than repeating myself, and questions that I'm thinking about currently. Happy to have a chat and answer any questions at the end. I think we do all the questions together, right? So yeah, I will leave it there. Thank you very much.
Thank you very much for this really clear talk. Exactly, we are having questions in the end, but yeah, looking forward to discuss this. Okay, then let's just directly come to our last speaker. This is Kaian Shahateet, and he just presented his PhD defense at the Polytechnic University of Madrid. And with him, we stay at the Antarctic Peninsula, where he has been assessing mass change, ice discharge, and ice thickness change using remote sensing as well and inversion modeling. And yeah, today he will focus on his last work on ice thickness changes. And yeah, welcome, Kaian.
Awesome. Thank you, Falk, for the presentation. Can you see my slides?
Yes, looks good.
Can you see my screen? Thank you for organizing this meeting, which is awesome. I think my presentation is really related to the one of Ben, which is a reconstruction of ice thickness of the Antarctic Peninsula ice sheet north of 7 degrees south, which is more or less the same region where Ben was doing his studies. I was supervised by Francisco Navarro, and co-supervised by Thorsten Seehaus and Johannes Fuss. This is part of my PhD that I recently defended in December. So yeah, let's start. I think I don't need to do a comprehensive introduction as Ben, because he did pretty well. But the region that I'm going to present is the Antarctic Peninsula ice sheet, which is the one highlighted in green. It has an area of 100,000 square kilometers, which is comparably small in relation to the whole Antarctica with 14 million square kilometers. But its sea level equivalent is close to the one of Canadian Arctic, which is today the most important contributor to sea level rise, with bigger area of 50% of the Antarctic Peninsula ice sheet. we selected this region due to the limited amount of studies, specifically for ice thickness. And also we did some ice charts that we're going to talk now. It was the motivation of our reconstruction, because when we performed the ice discharge, we saw that we had 5 different models available to calculate the ice discharge, and we saw that they weren't agreeing very well in terms of total ice discharge. So for that, we defined more than 300 flux gates, where we suppose that all mass is passing through these gates. We then use the discretization that we can see here in the equation. For that, we used a common velocity field from InView, and then the ice density and the spacing between the discretization was the same for the 5 different models. And here were only varying the ice thickness, which is the H in the equation. We had, as I said, we had 5 different models. The first is Karavik, which is a perfect plasticity approach. We also calculate the ice discharge of Rosen-Farinot, which is a shallow ice approximation. And then we had BadMap2 and BadMachine, which in this region is mostly interpolation. And then Deep BadMap is a neural network applied to the solution of BadMap2. We can see that there's a lot of spreading of the data of the calculations. For example, Karavik is 3 times larger than the calculation using BadMachine, and we can see by the standard deviation that the choice of the model to be used highly impact the final calculation of ice discharge. Here we can see the histogram of the ice thickness extracted along the flux gates. We see that Karavik and Hus and Farinot, they are very close in terms of distribution. They look similar, whereas BadMap2 and BadMachine, they are similar between them. But here we can see the number of zeros in the case of BadMap2 with 24% of zero ice thickness, but BadMachine doesn't have as large number of zero ice thickness. But when we do a further analysis, we can see that most of the values of BadMachine is between 0 and 1. So they are presumably underestimating the ice discharge as well as the BadMap2. And when we take a closer look into the deep BadMap data, there are a lot of negative values there, and I'm not going too much detail here to explain why there are some negative values in the calculations of the ice thickness of deep BadMap. But plotting the whole histogram of deep BadMap, we can see the large amount of negative values. In fact, it represents 44% of the ice thickness extracted from deep BadMap. I would like to point to our paper published in the Annals of Glaciology, where we estimated the ice discharge of the Antarctic Peninsula using different ice thickness data sets. There we concluded that Karavik and Rosen-Farinot, they are the more reliable reconstructions. They're physically based, but they use perfect plasticity and shallow ice approximation, which are not the most suitable approaches to be used in fast-flowing regions where there are basis lighting. And we also conclude that deep BadMap, BadMap2, and BadMachine, they're probably underestimating the ice discharge. This motivated our own reconstruction, where we used 2 steps approach. First, we have the input data, where we did some refinement, especially for the glacier outlines, and the thickness observations, where we removed unrealistic measurements, especially for the Operation Ice Bridge. We then enter into the first step, where we branch into 2 different approaches. The first is to solve the mass conservation where we solve for f that we are going to see in the next slide. We then use a cost function, as you cannot ensure the consistency between the input data. And then we convert from flux to ice thickness using the shallow ice approximation. And then we have a final ice thickness map using shallow ice approximation. In the other branch, we calculate the ice thickness using the perfect plasticity approach. This way, we also have a thickness map. We then pass to the second step, where we have velocity, reliable velocity field. We then solve the mass conservation equation directly to ice thickness. We again use a cost function to have a better result for both solution. And then we have two thickness map using shallow ice approximation and perfect plasticity. And then we merge them together to have a final solution. All of that was implemented in ice, and we did our calculations in the HPC of FAU in Germany. You might think that we are again using shallow ice approximation and perfect plasticity that we criticized before, but in our case here, we are using a second step where we think that the approaches used could fail. So here's the mass conservation equation that we use. Here we don't know the velocity, neither the ice thickness. Thus, we merge them together into a flux field variable. This way, the equation changes to this one, where we have the apparent mass balance equal to the surface mass balance minus the elevation change. And this way we can use the shallow ice approximation to invert from flux to ice thickness. We use the equation of perfect plasticity to convert from the geometry of the surface of the glacier and the driving stress of the material that we can infer from ice thickness measurements, such as the one of Operation Ice Bridge, to infer the ice thickness. In this case, we have two preliminary ice thickness maps. We then merge with the surface velocity, where we're gonna again solve the mass conservation, but this time the equation, the first version of the equation, where we can solve the ice thickness straight to h. This way we have a final ice thickness for both solution, and then we merge them together. This is an example of a glacier where we performed the second step. This is the Cellar Glacier. In magenta, inside the magenta region is fast flowing region where we solve the mass conservation using the velocity field. And then in the boundary condition in magenta, we use the ice thickness of the first step of shallow ice approximation and perfect plasticity. This is our final solution using shallow ice and perfect plasticity and the combination of both. The total volume calculated by the combination of both solutions is 27.7 thousand cubic kilometers, whereas the ice discharge is 97.7 cubic kilometers per year. If we compare our solution to the other 5 that we talked previously, our ice volume is really close to Husen-Farinotti. The ice discharge of the shallow ice approximation, the first step, was also close to Husen-Farinotti. It had a difference of 10%, but then when we applied the second step, we decreased the ice discharge a lot, but it's still closer to Husen-Farinotti than the other solutions. It's also worth to mention that our reconstruction for the total ice volume was close to the mean of the 6 models, and also the average discharge of the 5 models. Here we compare our results to Farinotti and others 2013, where he did a reanalysis of ice thickness measurements over the Flask Glacier. Here we only selected the 3 better points, the P1, P2, and P3, whereas we rejected P4 and P5, which were classified as bad data by Farinotti. Here we see that BedMap2 had the best solution with the lowest error of 29%, whereas our solution and the one of BedMachine was with 35%. And the other three models, they were close to 60% error. We also used the Starbuck Glacier data, ice thickness over Starbuck Glacier, to calculate the error of the different models. This time is Farinotti 2014, and this time they didn't do a reanalysis of the data. And it's we just use all of the data that they provide. And Karavik had the best solution with 37% error. We couldn't validate the solution of Jose and Farinotti because they used this data in their reconstruction. And our solution was with an error of 42%. All of the others were much higher than that. We then did a qualitative analysis. There's two regions that we would like to focus. Here is the first region. There's a lot of thickness measurements, and the second, there's not as many. Actually, there's almost no measurement here in the second region. So here we can see the solutions of Karavik and Farinotti in ours. Despite the difference between the absolute difference between the ice thickness, we can see that we reproduce the features of the Antarctic Peninsula, because here there's a plateau with an ice cap that flows through a steep terrain, and this ice falls and cliffs. So you expect a thinning of the glacier in this part, and then in the valley it gets flat again, and you would expect a thicker ice. We all reproduce that in our reconstruction. But then when we look into the solutions of BedMap2 and BedMachine, they also reproduce the Antarctic Peninsula plateau and the thinning when they pass through steep terrain, but they fail to reproduce the outlet glaciers in the valleys of the region. DeepBedMap, there's the same pattern. They reproduce the plateau and the thinning, but there's much more noise, and they also fail to reproduce the outlet glaciers flowing through the valleys. When we look into the second region, the same pattern happens to Karavik, Jose and Farinotti and ours. And I would like to highlight here the solution of BedMachine. They couldn't reproduce the solution, the Antarctic plateau. In fact, they were near zero in this region, and this is why we presume they are underestimating the ice discharge. Again, the BedMap have a lot of noise, but they kind of reproduce the plateau, and BedMap2 was, as previous, reproducing the plateau, thinning, and they failed to reproduce the valley glaciers. Some conclusions that we can draw from our work is that we successfully generated the ice thickness map. We did some improvements to the calculation I didn't mention, but we calculated different from the FUS 2019, 2017, which was the base of this calculation. Our solution is comparable to that of Jose and Farinotti in terms of ice discharge in total volume, and it's also comparable to Karavik in terms of qualitative analysis that we saw previously. We did some refinements of the input data, such as glacier inventory and the ice thickness data, and we could well reproduce the features of the region that we were studying. We would like also to say that improvement of the ice thickness would be beneficial for us. In this case here, I'm representing the Operation Ice Bridge data. Here we can see they vary a lot within the Operation Ice Bridge data. Here there's a distance of less than 5 meters, and they vary more than 900 meters. And the same happens if we compare the Operation Ice Bridge and Farinotti data, that they have a lot of difference. I would like also to highlight the importance of works of rings, for example, where they're intending to acquire bathymetry, but also ice thickness for the whole periphery of the Antarctica. And also, we would like to expand our solution in the future to include the southern part of the Antarctic Peninsula, and this is the Palmerland. So having a complete solution for the Antarctic Peninsula would be also beneficial for the community. That's all. Thank you very much for your attention.
Yeah, thank you for your interesting talk. And yeah, then it's already getting close to 11 p.m. for me, so I think we should directly jump into the questions. And yeah, are there any? Okay, Roland, you have one.
Hi. Yeah, another 3 very interesting talks. I have a question for Ben. Specifically, he was talking about this big acceleration of the Cadman Glacier. And you mentioned warmer ocean waters, I think, as a possible explanation. Have you looked at whether part of the mediation of that process might be sea ice or fast ice concentration or extent in that area? You're on mute, by the way.
Yeah, so I did. So the story of kind of the analysis of that's a lot longer than I have time to go into in this talk, so it could be its own talk. Sea ice in that bay wasn't fast sea ice for like a long period of time. It stays around for a few years. Sometimes it disappears in other years. The calving front that glacier had been stable for since the 80s until this acceleration event where it then retreated by 8 kilometers. So I didn't think that land fast sea ice had a role to play there. There were some other things that also led us to think it was ocean forcing. So the glacier had a sort of field confined small ice shelf, kind of ice tongue, just floating, and that had been thinning. You could see in cryosat altimetry data that had been thinning quite consistently. And then there was a region of like a speed minimum and compressive stress associated with a bed ridge, and the flow field when the glacier accelerated a lot actually changed in that area, and that sort of speed minimum associated with that ridge disappeared, became sort of continuous speed through that region, if you see what I mean. So we're quite convinced there was ocean warming leading to thinning of the glacier on that pinning point that caused that change.
So it's an unpinning situation.
Yeah.
Right. Okay. Thank you.
Right.
Okay. Are there any more questions? I would have a question to Elliot. On page 11, you showed like the mismatch between I think it was ice thickness and what you produced, and for the top to like northern glaciers it was positive or negative, and for the southern glacier vice versa. I was wondering, like, what does this tell us? Why, like, how does the including the basal friction law, like, yeah, change with these 2 glaciers?
So it was, yes, the bias of the velocity, and so for the 2 glacier of the north, the front has retreated since 1995, but for the glacier of the south, it has not retreated a lot. So it's why you have like a dissymmetry between these 2. And we also explain in the papers, and for the south one, you have quite a high bed. The bed is going around at this for the south glacier, and because of some extrapolation of the basal friction, it slowed down the glacier. Because yes, the basal friction is quite high at this, and only small change of the front position can change a lot the velocity.
Okay. Yeah. Thank you. Are there any other questions from the audience? Okay, Roland, you have another one?
Yes, it's just a follow-up on that Elliot's work. You described your variable sliding as parameterized in terms of distance, distance from the ice front. So is that recomputed if the ice front is retreating? Or are you just looking at a steady geometry?
Yes, I'm prescribing the front position. So yes, when it's rotating, I change the distance to the front.
Right. Did you contemplate looking at other ways of trying to mimic glacial effective pressure, involve concepts like the thickness above flotation, which obviously also has a sort of prescribed dependence on the distance from the front? Have you explored that?
Yes, I tried also with 8 above flotation, but because the initial surface is quite, yes, unknown at the beginning. We don't know it a lot. It leads to large instances, and the front position we know it quite well in 1985.
Okay, thank you. Ben, do you also have a question?
Yeah, I wanted to ask Kaian a question about the peninsula thickness data, because it's a problem that I've encountered in my work. I was wondering how, obviously there's a lack of ice thickness measurements from GPR, like that you already touched on, but how do the other limitations of data on the peninsula affect your modeling? So things like that surface mass balance isn't necessarily well resolved in a lot of the regional climate models, so the grid size, or a lot of the grounding line measurements for the peninsula are quite out of date because they're from ERS 1 and 2.
Yeah,
do those have an impact? And like just like new products like Bryce Noel's 2 kilometer
all of that have impact in our solution. Actually, the operationalized bridge, there's a lot of data, but as we saw, there are a lot of meaningful points with high ice thickness over mountain, including the surface mass balance, as you said, is really coarse for the region. So we need to do a downscaling, really aggressive, from 7.5 kilometers to 100 meters. The grounding line is not perfect to define the flux gates, for example. So yeah, the Antarctic Peninsula is really hard to model and infer the ice thickness or whatever you want to do in the Antarctic Peninsula. This is why we have large error, in fact.
Okay, thank you. Are there any last questions for today?
Yeah, I have a question in the chat.
Oh, sorry, I didn't see this one. Do you want to speak it out loud, or?
Yeah, it's a question to Benjamin. And it's, I mean, it's not a question, but more a comment that don't you think that your view of the mass losses from the Antarctic Peninsula is too negative in the sense, because you mentioned, for instance, Otosaka, which is the consensus approach, and I have just in front of me, I'm looking at the losses for the different periods. They seem quite stable since, I mean, of course, it increased after the ice shelf disintegration, mostly in the 2002, I think it was. But it has been quite stable for several decades, and on some particular points, like between 2012 and 16, then it even decreased. And then on the other hand, if you look at the, if you read at the projections from the last IPCC report, which are mostly probably based on Edwards and others from 2021, then, so I can read to you, is the model response of the Antarctic Peninsula to climate warming shows little detectable temperature dependence. And the reason is that model projections predict a virtual balance between increased size discharge and increased snowfall. And this is even more marked in the case of high emission scenarios, because in that case, even the snowfall accumulation increases dominate the mass losses. And even when they consider the effect of the collapse or possible collapse of the ice shelves in the models, they predict that there is little influence until the end of the century, because the surface meltwater is not projected to be sufficiently large to trigger ice shelf collapse, at least until the second half of the present century. So, I mean, I have read your first arguments just for motivation, and I think they are somehow maybe exaggerated or not. I don't know. It's my impression.
Okay. Yes, I guess maybe I'll start with the IPCC point you raised. I think to me that highlights the motivation to consider how forcings around the peninsula will change, right? Because they say that in those projections, increased ice discharge is balanced by increased precipitation. That's two large numbers, and if there's a difference between them, that could be quite significant, right? And I think the uncertainty of the balance between those two is something that's worth thinking about and investigating in more detail. There's certainly, you know, the behavior of surface melt and snowpack on longer time scales, in terms of like firn air depletion isn't necessarily linear, etc. So I think that, you know, that to me that's a reason that it's worth thinking about investigating. Because yeah, if you're relying on two big things to cancel out, that's quite an assumption. If you're slightly wrong about one of them, then you'd be quite wrong about the answer overall. So I guess I would say we shouldn't be complacent about that, perhaps. And then in terms of the ice discharge in the INBI work, I think, yeah, I was only really talking about ice discharge in my talk. So I'm not sure what the surface mass balance trend is exactly in the same period. It may be that some increased precipitation has cancelled some of those discharge changes out. I think that's an interesting point that links to the second point itself. Yeah, I would probably say I think that saying that it's exaggerated is a little bit unfair, in my opinion. I guess you said it was a comment, so that's my answer.
Yeah. Okay, no, for me, what is worrisome is, for instance, as Kaian has pointed out, these huge discrepancies between the different estimates of ice discharge, mostly based on the huge differences in the bed reconstructions. And when you look at the data, I'm really horrified. So I'm looking at, so you see sometimes how so many these flight lines from ice bridge, but then when you look at the actual numbers, many of them are just empty. So it's no data on them, especially in the northern Antarctic Peninsula. But then in other cases, you see ice bridge data incoherent with itself as huge, tremendous differences, doubling the thickness in the same point. Or when you compare this to the more recent estimates, which were ground-based and done with great detail, sometimes by Farinotti, for instance. So that is scary for me.
Yeah,
because I mean there are so huge uncertainties in this, which is okay.
Yeah.
Okay, thanks.
I think the 2 points are connected, because a lot of those assumptions about modelling the ice discharge from the peninsula into the future projections that the IPCC report talk about are making assumptions about the bed topography, based on data sets that, as Kaian's work shown, have a lot of discrepancies in them. Particularly if you say used bed machine, where there's huge amounts that are zero. Well, if you change the climate and the ice has no thickness, then it doesn't matter, right? In terms of mass balance. So I think actually the two things are linked in my mind, and they have relevance to each other. And I think as well, talking about going back to the INBI work as well, there's a big lack of mass balance assessments for the peninsula. So for the input-output method, there's only one data set in the INBI product. It's from Eric Vigneault. Altimetry, I think there's like 3 products in there, and then there's a few more gravimetry estimates, but that's very limited compared to how much coverage there might be in other places, or how many other data sets are generated, say, for West Antarctica or for Greenland. So I think that there's a shortage of data and estimates, and I think that's another reason to be motivated to study the peninsula.
Okay, thanks.
Okay, Roland, you have the last question, I would say, because it's getting quite late.
Yeah, sorry. It was really just provoked by that last discussion. And I think one of the important things that comes out of what we're seeing from Benjamin is, did any of those consensus opinions about what's going on here, do they even know that there's this strong seasonal variation in the ice velocities, which, since that's something that we have always assumed you just don't see in really cold places, does that suggest that the projections of future ice discharge in this area might be seriously different to a simple-minded projection, due to questions such as the one that Ben raised about why we're not seeing sudden slowdown connected to efficient basal hydrology network theories and so on. So I guess one can really worry that the future prospects for claiming to know what ice discharge will look like here. Certainly these observations are always great because they're real, suggest that describing what's going to happen in the future might be a challenge. Ben?
Yeah, I think, as I say, I find it difficult to imagine that if melt does reach the bed, that it would cause a huge discrepancy. But I think obviously it's a process that is important. It can also cause subglacial discharge, could also cause increased calving at the grounding line by undercutting the ice front. So I think perhaps there are some dynamics that might not be well captured, and the peninsula has other important aspects we need to think about, as well as just global sea level rise, like the glaciers and peninsula influence the ecosystem there quite heavily. It's a really diverse and productive part of the global ocean ecosystem. And I think there's some modelling studies recently that showed that melt and ice discharge from the peninsula can influence basal melting in West Antarctica as well. So I would make the argument that it's worth studying and it's worth thinking about. And I think it's an open question and it's worth investigating. I wouldn't claim to have the answer to how much it matters either way, but currently I don't think anyone knows, and I don't think it should be something that should be dismissed, perhaps.
Okay, great, thank you. And then with these realizing what we need to study next, I would close today's meeting and thank especially thank the speakers for presenting today. And and I also want to introduce the next week's seminar, which is a sea ice seminar about overwintering in Antarctica to observe the sea ice, and it will be given by Vishnu Nandan. And would be happy to see a lot of you at the next seminar. And with this, thank you everybody for listening, and thank you again for the speakers. And hope to see you next time.
Thank you for the opportunity.
Bye.
Bye. Thank you.
Bye-bye.
Bye.
Thank you. Bye.